There are worlds out there with no sun, no star warming them, no light touching their surfaces, no solar system surrounding them. Just a planet, alone, in the dark, between the stars, drifting through the cold of interstellar space at tens of thousands of miles per hour, with nowhere to go and nothing to orbit. These worlds have been traveling in darkness for so long that the stars they once circled may have long since burned out and died. They have no mornings. They have no seasons caused by proximity to a star. They have no day, no night, only a permanent unbroken darkness, with the faint and distant smear of the Milky Way above them and nothing else. We call them rogue planets, and there may be more of them in our galaxy than there are stars. Let that settle for a moment. For every star you can see in the night sky, for every sun in the Milky Way's population of somewhere between 100 and 400 billion, there may be one or more free-floating planets wandering alone through interstellar space. The galaxy, which we tend to think of as a collection of stars with planets around them, may actually contain more unbound, starless worlds than it contains stars. The planets orbiting stars may be the minority. The dark wanderers in between may be the majority. And until very recently, we barely knew they existed. This is not science fiction. The first confirmed rogue planets were identified in the late 1990s and early 2000s. Subsequent surveys have found dozens, then hundreds of candidates. And with the James Webb Space Telescope, operational since 2022, astronomers have detected rogue planet candidates in the Orion Nebula in numbers that genuinely startled the people analyzing the data. Objects that appeared to be Jupiter mass or smaller, free-floating, not bound to any star, drifting through one of the most famous star-forming regions in the sky. Some of these newly detected objects appeared to be in pairs, orbiting each other as binary systems, a configuration that raises deep questions about how they formed. The rogue planet population of the galaxy is not a curiosity or an edge case. It is, if current estimates hold, one of the dominant features of the galactic census of worlds. To understand rogue planets, how they form, what they are, what they might be like to stand on, you need to first understand how planets form in the conventional sense, and then understand all the violent ways in which that process can go wrong, because the story of rogue planets is in large part the story of planetary formation's violent failures and catastrophic successes that went too far. Stars form from the collapse of giant clouds of gas and dust, molecular clouds, enormous aggregations of hydrogen and helium, and traces of heavier elements drifting through the galaxy. When a region of such a cloud reaches sufficient density, gravity begins to win against the thermal pressure that had been holding the gas up, and the cloud begins to collapse. As it collapses, it fragments into smaller clumps, each of which forms an individual star. Within the disk, microscopic dust grains collide and stick together, growing into millimeter-sized aggregates, then centimeter-sized pebbles, then meter-sized boulders, then kilometer-sized planetesimals, then moon-sized protoplanets, and eventually full-sized planets. It is a hierarchical, violent, chaotic process that takes millions of years and involves an enormous amount of collisions, mergers, near misses, and gravitational interactions between the growing bodies. The final architecture of a planetary system, which planets end up where, how many survive, how their orbits are arranged, depends on the initial conditions and on the countless gravitational interactions that occurred during the formation process. And those gravitational interactions are where rogue planets come from, at least in one of the dominant proposed mechanisms. Planet formation is not tidy. As multiple planets grow in the same disk, they interact gravitationally with each other and with the disk itself. Giant planets can migrate inward or outward from their formation locations. Close encounters between planets can result in one being ejected entirely, flung out of the system at high velocity by the gravitational slingshot effect of its interaction with a larger sibling. Computer simulations of planetary system formation show that ejection events are common, not rare. Many simulations of solar system-like architectures produce systems where one or more planets are lost to ejection before the system settles into its final configuration. Our own solar system may have ejected planets. Some models of the early solar system's evolution, in particular the NICE model and its variants, which attempt to explain the orbital arrangement of the outer planets, suggest that the giant planets underwent a period of gravitational instability early in solar system history, during which their orbits shifted dramatically. Some versions of these models work best if there were originally 5 giant planets rather than 4, with the 5th being ejected in the gravitational reshuffling. If this is correct, there is a world out there in interstellar space, Perhaps a Neptune mass or Uranus mass planet that once orbited our own sun and was flung into the dark billions of years ago. It is our sibling, and it is somewhere out there in the galaxy right now, alone and frozen, with no way of knowing it was once part of a family. The gravitational ejection mechanism is one way rogue planets form, but it is not the only way, and this is where the story gets more interesting. The other major formation pathway does not involve ejection from a planetary system at all. It involves rogue planets forming the way stars form, directly from the collapse of small gas clouds, in isolation, without ever being part of a disk around a star. When a giant molecular cloud fragments and collapses to form stars, the fragments that produce individual stars have typical masses of a solar mass, or more. But the fragmentation process has a lower limit, or rather the lower limit of what can successfully collapse and sustain nuclear fusion to become a true star. The minimum mass for sustained hydrogen fusion is about 8% of the Sun's mass, or about 80 Jupiter masses. Objects below this threshold never ignite as true stars. They are called brown dwarfs if they are massive enough to fuse deuterium, or they are substellar objects or rogue planets if they are smaller. The fragmentation of molecular clouds can produce clumps of gas that are below the stellar mass limit, clumps that collapse under their own gravity but simply do not have enough mass to ever light up as stars. They become free-floating substellar objects, formed by the same mechanism as stars but smaller, born in isolation from the beginning, never bound to any stellar system. The distinction between a rogue planet formed by ejection from a planetary system and a rogue planet formed directly from a cloud collapse is not just interesting in terms of origin, it has physical implications. An ejected planet would have a bulk composition and internal structure reflecting its history of accretion in a protoplanetary disk. It might have a rocky core overlaid by deep layers of hydrogen and helium, analogous to Jupiter or Saturn, or it might be a rocky or icy world, more analogous to Earth or Neptune, depending on its original position in the disk. A directly collapsed rogue planet would form from the primordial composition of the gas cloud, overwhelmingly hydrogen and helium, with whatever trace heavy elements were in the cloud, but without the compositional gradients and layered structures that develop through disk accretion. Distinguishing between these two populations observationally is one of the key scientific goals of rogue planet research. Finding rogue planets in the first place is extraordinarily difficult, which is why we went so long without knowing much about them. Stars and planets with stars around them are identifiable because they emit light. Starlight illuminates the planets, and the planets reflect it, and even though that reflection is faint, it is something. Rogue planets in the cold of interstellar space emit almost no light. A Jupiter-mass rogue planet that has been wandering alone for billions of years has long since cooled from whatever temperature it had when it formed. It does not reflect starlight because there is no nearby star. It emits only the faint heat of its own slow cooling, thermal infrared radiation at temperatures that may be only a few dozen degrees above absolute zero for old, cold rogues. Detecting such objects requires infrared telescopes of extraordinary sensitivity pointed at the right part of the sky. And even then, distinguishing a cold rogue planet from a background object requires careful follow-up. The James Webb Space Telescope has been transformative in this regard because it is the most sensitive infrared space telescope ever built, capable of detecting objects far fainter and cooler than anything its predecessors could see. The detections in the Orion Nebula announced in 2023 included objects as small as 1 Jupiter mass, the lower boundary of what we typically call a planet, free-floating in the nebula, some of them paired with each other in binary configurations that had never been anticipated. These Jupiter-mass binary objects, which the team nicknamed BOOMs, are particularly puzzling because current formation models struggle to explain how objects so small could form directly from cloud collapse, and yet they are clearly not ejected planets because they are bound to each other and exist in a very young star-forming region, where there has not been time for planetary systems to form and then violently eject members. The Jumbo discovery was a genuine scientific surprise. It suggests that either our understanding of the minimum mass for direct cloud fragmentation needs revision, that molecular clouds can somehow produce fragments far smaller than theory predicts, or that there is a formation mechanism we have not yet identified. Or perhaps the disk ejection process in very young, dense stellar environments like the Orion Nebula operates on timescales far shorter than expected. The honest answer is that we do not know, And that is itself an indication of how much the discovery of rogue planets in numbers is pushing the boundaries of our models. The statistical estimates for the total number of rogue planets in the Milky Way have been updated repeatedly as detection methods have improved, and each update has tended to push the number higher. Microlensing surveys, which detect rogue planets by observing the gravitational lensing effect they produce when they pass in front of background stars, have been particularly important. When a massive object passes between Earth and a more distant star, the object's gravity bends the light of the background star and temporarily brightens it. The shape and duration of this brightening depends on the mass of the lensing object, and very brief, very faint microlensing events are consistent with Earth mass or smaller free-floating objects. Surveys using this technique have found microlensing signals consistent with a large population of Jupiter mass and smaller free-floating planets, with some analyses suggesting that low-mass rogue planets could be extremely common, potentially numbering in the trillions in the Milky Way alone when you extend the count to Earth mass and smaller objects. Trillions, not billions. In the Milky Way, which has something like 100 to 400 billion stars, each of which we now know typically has at least one planet in orbit, the population of free-floating planets may dwarf the population of bound planets by a significant factor. The galaxy is full of dark worlds we never knew were there. Now let us talk about what it would actually be like on one of these worlds. This is where the story becomes both beautiful and haunting, because the surface experience of a rogue planet, if you could somehow be there, if some form of existence were possible, would be utterly unlike anything in our solar system. Consider first the sky. On Earth, the sky is dominated by the sun, which is so bright that during the day it washes out everything else. At night, we see stars because the sun is on the other side of the planet. On a rogue planet, there is no sun. The sky, at all times, in all directions, is the night sky. The stars, wherever the rogue planet happens to be in the galaxy, are always visible. The full glory of the Milky Way is always present, uninterrupted, stretching across the entire sky. Whatever atmosphere the planet has does not scatter any strong local light source, so unless the planet's own atmospheric chemistry produces some glow, the stars are always sharp and clear. If the rogue planet is in the disk of the Milky Way, the galactic center is visible as an extraordinary band of light spanning the sky. If it is in the galactic halo, far from the disk, the entire galaxy spreads below it like a luminous island in the dark. The sky of a rogue planet is, in one sense, the most beautiful sky imaginable, uninterrupted by any local sun, the full architecture of the galaxy permanently on display. But the light reaching the surface from those stars is almost nothing. Stars are bright as individual points, but as sources of illumination spread across a planet's surface, the combined light of all stars in the sky provides only a tiny fraction of the light that the sun delivers to Earth. The surface of a rogue planet, even with 1 billion stars visible, is dark in a way that has no true analog in human experience. It is darker than a moonless night on Earth, which is itself dark enough that human eyes struggle. It is darker by orders of magnitude. If any organisms lived on the surface of a rogue planet relying on photosynthesis-like processes using starlight, they would need to be extraordinarily efficient, capturing and using energy at a level far beyond anything terrestrial photosynthesis achieves. The temperature of a rogue planet's surface, absent any stellar heat, would be determined primarily by the planet's own internal heat and the background temperature of space, which is about 2.7 Kelvin, just a few degrees above absolute zero. For a planet like Jupiter, interior heat from gravitational contraction and residual formation energy would keep the planet warm in an absolute sense, with internal temperatures reaching thousands of degrees, but the radiation of this heat to space over billions of years cools the object progressively. An old, Jupiter-mass rogue planet might have a surface temperature, insofar as gas giants have a surface, in the range of tens of Kelvin, or perhaps a bit warmer if it is young enough to still retain significant internal heat. The distinction between a young and an old rogue planet in terms of surface temperature is significant. A freshly ejected or recently formed rogue planet, still warm from its formation heat, might have surface temperatures of hundreds or thousands of Kelvin. A billion-year-old rogue is much colder. For rocky rogue planets, Mars-sized or Earth-sized worlds flung from their systems, the situation is particularly interesting from the perspective of the possibility of life. A rocky planet without a star seems at first glance like the most inhospitable possible environment. No sunlight means no photosynthesis, no warm surface, no liquid water on the surface. The surface would be bitterly cold, perhaps only slightly above the temperature of space, if the planet has no significant internal heat left and no thick atmosphere. It would be barren and frozen in a way that makes Antarctica look welcoming. But here's where the story takes a profound turn. Not all of a planet's heat comes from its star. Planets generate internal heat through multiple mechanisms. The original heat of formation, the energy released as material accreted and impacted during planetary construction, is stored in the interior and radiated out slowly over billions of years. Radioactive decay of elements like uranium, thorium, and potassium-40 in the rocky interior provides a continuous source of heat that does not depend on the star at all. Earth's interior is warm primarily because of these radioactive elements, and this internal heat drives plate tectonics, volcanism, and the geothermal heat that seeps through the ocean floor in hydrothermal vent systems. Here on Earth, the hydrothermal vent ecosystems are among the most extraordinary discoveries in biology. In the 1970s, oceanographers diving in the deep Pacific discovered vents in the ocean floor where superheated water, enriched with minerals and chemicals, pours out of the rock into the cold, dark, sunless, deep ocean. Around these vents, ecosystems of extraordinary richness exist. Tube worms, shrimp, crabs, fish, mats of bacteria, all in a place where no sunlight ever reaches. These ecosystems are powered entirely by chemical energy from the geological interior of the Earth. They have no dependence on the sun whatsoever. They are, in a very real sense, a preview of what might be possible on worlds with no stars. On a rocky rogue planet of Earth-like size and composition, the radiogenic heat from the interior, the heat from uranium and thorium decay, would persist for billions of years. If the planet had water, comets and asteroids deliver water to planets during formation, and there is no reason an ejected rocky planet would not retain its water. The internal heat might keep that water liquid beneath the surface, or beneath a thick layer of ice on the surface, for billions of years, even in the complete absence of starlight. A global subsurface ocean kept liquid by internal heat, covered by a thick ice shell that insulates it from the vacuum of space, could potentially persist for the entire current age of the universe and beyond. And in that ocean, in the dark and the warmth of geothermal heat, around hydrothermal vents, the conditions that we now know support rich ecosystems on Earth might exist. Not on the surface, not in sunlight, but deep inside, in the warmth of the planet's own geology, in water that has not seen a star in billions of years. Chemistry could be happening. Complex chemistry. Chemistry that on Earth eventually produced life. We do not know whether life requires a star. We assumed it did for most of human intellectual history, and the assumption seems so obvious it was barely stated. But the discovery of hydrothermal vent ecosystems, and the subsequent recognition that the energy source for life does not have to be sunlight, has cracked that assumption open. It has forced a genuine reckoning with the possibility that life, if it exists elsewhere, may exist in places we never thought to look. And rogue planets are perhaps the most dramatic example of a category of world we never considered as a potential habitat, but which, under scrutiny, turns out to not be obviously uninhabitable. There are additional heat sources available to rogue planets beyond radiogenic decay. Tidal heating, the frictional heat generated in a moon's interior as its orbit is distorted by the gravity of a massive parent body, is responsible for the extraordinary volcanism on Jupiter's moon Io and for the subsurface ocean of Enceladus. If a rogue planet has moons, and there is no reason ejected planets would necessarily lose their moons in the ejection process, tidal interactions between the planet and its moons could provide additional heat. A rogue planet with a large moon, on a slightly eccentric orbit, could sustain tidal heating in its interior for billions of years, providing warmth in addition to the radiogenic contribution. Add to this the insulating effect of a thick atmosphere. A rocky rogue planet with a massive hydrogen and helium atmosphere, captured during formation in the disk, retained because the planet is cold and the atmosphere molecules do not have enough energy to escape, could trap even the small amount of geothermal heat being released from the interior. A sufficiently massive hydrogen atmosphere could in principle maintain surface temperatures warm enough for liquid water even on a planet with no star, through a kind of geothermal greenhouse effect. A paper published in 2020 explored this possibility quantitatively and found that an Earth-mass rogue planet with a hydrogen atmosphere roughly 100 times the mass of Earth's current atmosphere could sustain surface temperatures near the freezing point of water, through geothermal heat alone, in the complete absence of any star. Not comfortable by human standards, but warm enough for liquid water. Warm enough, potentially, for chemistry. For life, the implications are staggering. If rogue planets outnumber stars in the galaxy, if there are trillions of free-floating worlds wandering between the stars, and if even a small fraction of those worlds are rocky, water-bearing, and retain enough internal heat to support liquid water, then the number of potentially habitable environments in the Milky Way may be far larger than estimates based purely on the habitable zones around stars would suggest. The habitable zone concept, the range of orbital distances from a star where liquid water can exist on a planetary surface, has been the organizing principle of the search for life in the universe for decades. It privileges sunlit worlds, it assumes the star is the heat source, and it may be wrong, or at least dramatically incomplete, as a framework for thinking about where life might exist. Rogue planets do not have habitable zones. They have habitable interiors, and there may be far more of them than there are star-warmed worlds. The search for rogue planets is about to enter a new era. The Nancy Grace Roman Space Telescope, NASA's next major space telescope after JWST, is designed in part with rogue planet science as a primary goal. Roman will conduct a wide-field microlensing survey of the galactic bulge, the dense central region of the Milky Way, monitoring hundreds of millions of stars simultaneously for the brief brightening events caused by intervening masses. It will detect thousands of microlensing events, including events consistent with Earth mass and smaller rogue planets, building a statistical census of the free-floating planet population that will be transformative for our understanding of how many rogue planets exist and what their mass distribution looks like. Current microlensing surveys, limited by the smaller collecting areas and narrower fields of view of ground-based telescopes, are already suggesting that low-mass rogue planets are abundant. Roman will quantify that abundance with a precision that current data cannot approach. JWST's infrared sensitivity is also being used systematically to search for rogue planets in nearby star-forming regions. Not just Orion, but other nebulae within a few hundred light-years where the young age of the stellar population means rogue planets formed there would still be relatively warm and bright in the infrared. The survey of Orion that found the jumbos in 2023 was, in part, a proof of concept for this approach, and follow-up surveys in other regions are underway. As this infrared census grows, we will develop a much clearer picture of the mass function of free-floating planets, how many there are at each mass, and this will help distinguish between the formation mechanisms. The Euclid Space Telescope, the European Space Agency mission launched in 2023 with the primary goal of mapping the large-scale structure of the universe to study dark energy, is also expected to contribute to rogue planet science as a secondary benefit. Its wide-field survey of the sky will capture microlensing events in addition to the cosmological data it is primarily designed to collect, providing another independent dataset on the rogue planet population. In addition to photometric detection through microlensing and infrared surveys, there is the tantalizing possibility of detecting rogue planets through other means. If a rogue planet has a significant magnetic field, as Jupiter does, generated by its rotating conducting interior, it might produce detectable radio emission through processes analogous to what creates the radio aurora of Jupiter. Rogue substellar objects, including massive rogue planets, have already been detected in radio wavelengths, demonstrating that this detection method is physically viable. Future radio surveys, including those being conducted with the Square Kilometre Array, may identify rogue planets through their radio emission in addition to all the other methods. The direct imaging of rogue planets, capturing actual photographs of them rather than inferring their existence through indirect methods, is another frontier that JWST is beginning to open. The Orion jumbo detections were essentially direct images. JWST resolved them as individual point sources distinct from the background. As JWST surveys more regions and as future telescopes with even higher angular resolution and infrared sensitivity are developed, the direct imaging catalog of rogue planets will grow from the handful currently known to potentially thousands of confirmed objects, each of which can be followed up with spectroscopy to determine its atmospheric composition and temperature. Spectroscopy of rogue planet atmospheres is one of the most scientifically exciting possibilities in the field. If we can obtain spectra of enough rogue planets, analyzing the light they emit in different wavelengths to determine what molecules are present in their atmospheres, we can learn about their compositions, formation histories, and physical states in ways that indirect detection methods alone cannot provide. For very cold rogue planets, the atmospheric chemistry might include water ice clouds, methane, ammonia, substances that are present in the outer solar system but difficult to study in the context of planets around bright stars because the stellar light overwhelms the planetary signal. A rogue planet has no star to overwhelm it. Its spectrum is its own, undiluted, and the atmospheric chemistry can be read directly. In the longer term, the scientific value of rogue planets extends well beyond simply cataloging how many there are. They are physical laboratories. Because they are not irradiated by a nearby star, their atmospheric and surface chemistry reflects purely internal processes in cosmic ray bombardment, without the complicating factor of stellar irradiation. Understanding the chemistry that develops in these conditions is relevant to the broader question of the origin of organic molecules in the universe, because interstellar space is in fact rich in complex organic chemistry. The interstellar medium contains hundreds of confirmed molecular species, including some amino acid precursors, and rogue planets wandering through this medium over billions of years would accumulate and process interstellar material in ways that might differ significantly from planets sheltered within stellar systems. There is a philosophical dimension to rogue planets that is worth sitting with. We have always thought of planets as secondary objects, the things that orbit stars, defined in relationship to stars, studied in terms of how they interact with their parent star's light and gravity. The first definition of a planet in the modern astronomical sense, adopted by the International Astronomical Union in 2006, the same definition that demoted Pluto, includes as one of its criteria that a planet orbits a star. By this definition, rogue planets are not technically planets at all. They are something else. Something that does not fit neatly into the existing ontological categories. This definitional awkwardness reflects a deeper truth, which is that our conceptual framework for understanding the objects in the universe developed in the context of a very limited observational sample, primarily our own solar system and, later, the exoplanet systems that telescopes began detecting in the 1990s. All of those systems involve planets around stars. The existence of large numbers of free-floating planetary mass objects forces a reconsideration of what planets fundamentally are. Are they defined by their relationship to a star? By their formation mechanism? By their mass? By their composition? Different answers to these questions produce different classification schemes, and the debate over terminology is actually a proxy for a much deeper debate about how planet formation works and whether the objects we call planets are one category or several. What is clear, regardless of terminology, is that free-floating planetary mass objects are real. They are common, and they are a major component of the galaxy's inventory of matter that we did not adequately account for before. The galaxy is darker and more crowded with worlds than the star-centered picture suggested. In between every pair of stars you can see in the night sky, there may be multiple planets wandering in the dark. Worlds that have never seen a star, or that saw one once and were flung away from it in the violent early history of their system, left to drift alone through the cold between the stars for billions of years. Think about what it would mean to stand on such a world. If there were a surface to stand on, a rocky rogue planet, perhaps, warm enough below the surface ice for liquid water but frozen and dark at the surface, you would stand in absolute darkness, except for the stars. The Milky Way would be vast above you, stretching from horizon to horizon if the planet's atmosphere permitted it. You would feel the faint warmth seeping up from the rock beneath your feet, the last residual heat of a world cooling slowly into the dark, powered by the decay of radioactive atoms that have been ticking since the planet formed. There would be no wind driven by solar heating, though there might be atmospheric circulation driven by geothermal heat rising through the ice. The silence would be total. There is no star nearby. There is no solar wind creating auroras, no tidal heating causing volcanism on the surface. Just the long, slow cooling of a world alone in the dark. And yet beneath the ice, perhaps kilometers below, where the geothermal heat has kept the water liquid, there might be something. Chemistry happening in the dark, minerals dissolving and precipitating, temperature gradients driving convection. And if the right chemistry happened, if the conditions aligned in the way they apparently did on a small rocky world orbiting a yellow star 4.5 billion years ago, there might be more than chemistry. There might be something reaching toward complexity, toward organization, toward whatever it is that separates life from non-life. We do not know if this is happening. We have no way yet of detecting it, even if it were. But the fact that the question is not obviously absurd The fact that the conditions for life as we understand it from the one example we have could plausibly exist on a world with no star is one of the most extraordinary realizations in modern astrobiology. The universe may be teeming with life in places we never thought to look. The planets orbiting stars in their habitable zones may be the visible, sunlit minority of inhabited worlds, while the dark wanderers, the trillions of rogue planets scattered through the galaxy, host ecosystems in their interiors that we cannot see and have not yet found the tools to detect. The galaxy is not what it looks like. When you look at the night sky and count the stars, you are seeing the lit-up fraction of a much larger population of objects. For every star, there may be one or more dark worlds drifting through the space around it, not orbiting it, not bound to it, just passing through, or traveling on ancient trajectories that take them nowhere in particular, on timescales that exceed the age of most of human civilization multiplied by factors so large they lose meaning. Those worlds are out there right now, in the space between our solar system and the nearest star, in the space between every star in the galaxy, in the vast and dark and cold interstellar medium that we think of as empty but which may in fact be filled with worlds. We found them because we looked carefully at the way starlight bends when something massive passes in front of it. We found them because we built a space telescope sensitive enough to detect the heat of young, recently formed objects in star-forming nebulae. We found them hiding in the infrared, invisible in ordinary light, their existence implied by mathematics and confirmed by the most sophisticated instruments humanity has ever constructed. And what we found suggests that our map of the galaxy has been missing most of its contents all along. The galaxy is not a collection of stars with planets attached to them. It is a collection of stars and planets and dark wandering worlds. And the dark wandering worlds may be the most numerous inhabitants of all. There are trillions of rogue planets in the Milky Way. They have been there since the galaxy was young. They will be there long after the stars around them have burned out and died. They drift in the permanent dark, alone, neither knowing nor being known. Until now, when a species on one small world around one ordinary star built instruments sensitive enough to detect their faint heat and the subtle bend of starlight that marks their passage. We noticed them. We counted them. We began to ask what they are like and whether they might harbor life. That is the most human thing imaginable. To look into the dark and notice what is there. To ask questions about worlds that have never seen a sun and may never be visited by anything other than light from 100 billion distant stars. To care about the answer. The rogue planets did not need us to discover them to be real. They have been wandering through the galaxy for longer than the Earth has existed. But now they are known, and the knowing changes something, not about the planets, but about us. About the scope of what we consider when we ask where life might be. About the size of the universe we feel ourselves to be part of. The dark is full of worlds. We are only beginning to count them.